Okay, it's time for start. Welcome everybody. I'm Goran Popovic from the Faculty of Physics, Belgrade, and I will be chair of this, the second morning session. Our first lecture comes from Croatia, Zagreb, from Institute of Physics. And the headline of his lecture is Cavity Ring Down Spectroscopy as a Tool for Plasma Diagnostics. Niksha, please start with your lecture.
Okay, thank you, Mr. Chairman, for a nice introduction. Thank you for organizers for invitation to this virtual meeting. So my name is Niksha Krstulovic. I'm coming from Zagreb, from Institute of Physics, and my today's topic will be on application of cavity ring down spectroscopy for diagnostics of plasmas, where we will put focus on mostly on laser-produced plasmas. But in our laboratory, we're studying different kinds of plasmas, so besides laser plasmas, which can be produced in vacuum gases and even in liquids for synthesis of colloidal solutions of nanoparticles. We are also studying radio frequency plasmas, atmospheric pressure plasma jets, and plasma jets at lower pressures. So laser plasmas are a very interesting medium because they can be source of photons from a broad range of wavelengths, then source of ions, atoms, and molecules, and the nanoparticles. What makes that plasmas as an interesting medium for the wide variety of applications, just to name few, maybe most distinctive is laser-induced breakdown spectroscopy for sample analysis, for characterization of materials. Such system is now employed in the Martian rover to explore Martian atmosphere and Martian surface. Then also very frequent application is of laser plasmas is in the form of path laser deposition for production of thin films for photovoltaics, for example. Then plasma can be a very interesting source of EUV radiation for development of photolithography of new generation, where instead of using laser, when we use EUV radiation, then resolution of printed structures can reach sub 10 nanometer range. Then plasma can be also used as a medium for generation of high harmonics for development of tabletop X-ray attosecond lasers, as a source of nanoparticles for microstructuring, and as tabletop accelerators. Laser plasma is produced via process of laser ablation, which is by definition mass removal by coupling laser energy to a target material. When absorption takes place from electrons, then they are excited, they are then collide with the lattice and spreading energy, what cause increase of surface temperature, increase of pressure, and because electrons leave the target, there is also accumulation of positive charges, what actually result in Coulomb explosion. So this is very energetic process, and we know that ablation then is that is stoichiometric process. That means that stoichiometry of the target is then reflected into the stoichiometry of the plasma. If we talk about the nanosecond laser ablation with nanosecond laser pulses, then delivered power is in range of megawatts. If ablation takes place with femtosecond pulses, then we are talking about terawatts. So that is very, very energetic process, and irrespective of the bounding of different materials in the lattice, the stoichiometry will be preserved. Typical collisional time between electrons and the lattice is in a range of 10 to the power of -13 of picoseconds, what means that during the course of a nanosecond laser pulse, there is lots of time for collisions, but during femtosecond ablation, collisions are very rare. So there is no heat diffusion. So with nanosecond ablation, we are producing such little bit irregular structures, but with femtosecond aberration structures can be very, very regular. Once when plasma is produced, it involves in time and space, and then we want to monitor all those processes, all those stages of plasma formation. So in the beginning, there is just continuum radiation, then in our spectra appear ions, atoms, and molecules, and if plasma is then produced in an atmosphere of some background gases, then we can also study formation of new molecules due to collisional processes. Using cavity ring down spectroscopy, we will see that we can do complete then temporal and spatial mapping of plasma constituents. So what's the difference between classical absorption and cavity ring down absorption? Classical absorption principle relies on the fact that actually we are measuring a ratio of intensities of incoming light and transmitted light, which is strongly affected by the source noise. This is very limiting factor because lowest particle number density is then depends on the difference in intensities, which is then affected by noise. But the other thing is also what is also limiting factor is that there is a relatively short absorption path length, which can be partly overcome by multipass cell. And if you have very stable source, at the end of the day, the sensitivity can reach ppm range, not more. Cavity ring down spectroscopy, by definition, is highly sensitive optical spectroscopic technique that enables measurement of absolute optical extinction by samples that scatter and absorb light. So experimental setup for cavity ring down spectroscopy is actually based on the optical resonator defined by two highly reflective mirrors. There is a tunable laser source, target, plasma, and photomultiplier tube or some other detector, which can be also CCD camera. And once when laser pulse enters the cavity, it oscillates back and forth many times, increasing absorption path length in some perfect cases up to 100 kilometers. In our case, this is hundreds of meters, but however, it significantly increases sensitivity due to the fact that we have hundreds of meters of absorption. Upon each reflection, a small fraction of light is leaking out to the detector, and in case when there is no any absorption or scattering, we are measuring with our photomultiplier single exponential decay. But in the case that we have absorption in the cavity axis, then decay will be faster. So actually we are measuring lifetime of photons which they spent in the resonator. So instead of measuring intensity, that is crucial advantage of cavity ring down over the classical absorption, together with the, of course, increased absorption path length. So cavity ring down is based on measuring time, not intensities. This is our signal measured by photomultiplier. We call it waveform. In semi-logarithmic scale, single exponential decay is actually a straight line. This is the case. When we have some absorption, which is time independent, then the slope of the line will be steeper. But in our case, we are talking about laser-produced plasma, which density is not constant in time. So we are talking about time-dependent absorption. But however, we can divide that signal into what we call time windows. And within time windows, we can approximate that plasma density is not changing. So we can apply actually time-independent case. This is a simple formula to calculate cavity loss or absorption coefficient just by knowing length between the mirrors, absorption length, this is speed of light, and by measuring time of photons for non-resonant and the resonant case when wavelength is tuned to some transition. So actually, the higher the the slope of this curve, the higher is the absorption. So actually we are measuring difference between slopes between non-resonant and resonant cases, between particular time windows, and by the fact that we can divide our signal in time windows, we have then temporal resolution of our measurement. So in each window, we can then get spectra for each individual species which is present in plasma. And of course, cavity ring down spectroscopy is not qualitative but quantitative technique, because it allows us to measure absorption coefficient in inverse centimeters and in absolute units, which allow us then to determine concentration of particular species in plasma. Okay, this is the case when we perform the ablation of manganese into the atmosphere of methane, and then we evaluated signal between the time windows, and we see that in the beginning, in the middle stage of formation, there is manganese molecules between first 250 nanoseconds. Then we can detect manganese hydrogen molecules. Then in some later time, we can detect C2 molecules, and at the end, there is no plasma. At least there is no plasma in the optical axis, or we call it also detection axis. So this is, in this way, then we can study dynamics of species in plasma. This comparison with cavity ring down signal and classical optical emission spectroscopy, where in classical emission spectroscopy we cannot see manganese hydrogen molecules or C2 molecules because they're not electronically excited, so they're not visible for emission. Cavity ring down is based on absorption, so we can also detect ground state features and get more complete picture on what's going on in plasma. Once when it gets spectra, and if we transfer wavelengths into frequency domain, we can easily calculate concentration of number density of particular species just by using this simple formula. When this is number density and this is integral of absorption line, these are some tonic constants. And how it looks, for example, upon ablation of titanium in vacuum, then we can monitor concentration of titanium in time. Of course, in absolute units. Moreover, we can actually move our plasma with respect to detection axis. So this is top view, so left and right and up and down, which actually give us a possibility to do two-dimensional mapping of the plasma, and together with the possibility to evaluate signal in time windows, and by the fact that plasma is axially symmetric, we can do then to complete three-dimensional and temporal mapping of all species in the plasma form. This is the example, a different position. We monitored actually concentrations of titanium in our laser plasma. These are some numbers. Yeah. We can also do velocity measurement of ablated species. That's also very easy because we can move. Sorry, I don't see cursor. Here it is. We can change the distance between the target surface and the detection axis. And at each position, we can measure the arrival time, so time which ablated particles needs to reach the detection axis. That arrival time is defined here. That is time when these two slopes for non-resonant and the resonant case start to differ. That means that we have particles in the cavity axis. We can do it for ablation under some background pressures. Here is the case of ablation of graphite into the atmosphere of H2 molecules for different pressures. And we can see here that there is some saturation, so So there is some distance which particles may reach, and after that there is no plasma actually. And by using direct force model, maybe some other models where we can apply sometimes, we can then calculate the deceleration factor, and this here factor d0, which is actually maximal distance which particles may reach with respect to target surface. In vacuum, there is free expansion of ablated species. Here we perform the ablation of lithium aluminum hydride target in the vacuum, and then we monitor velocities of all species, and you can see that these have some kind of time of flight nature because lighter species are much faster. For example, lithium is much faster than aluminum hydride molecules because this one is much steeper. By the fact that cavity ring is a sensitive technique, there is also room to improve our analytical capabilities. So we performed so-called dual or double pulse laser ablation when we use two laser pulses with separated in time to create plasma. These are actually emission spectra, which shows when was the difference between spectra obtained just by one laser, just by second laser, and with both lasers with optimized time delay, and it's obvious that sensitivity and that it's much better, and that we improve the analytical capability by using dual pulse laser ablation. Time delay should be optimized because for very short time delays, second pulse is screened by the firstly created plasma, so there is no effect. And for very long times, target which is preheated by first pulse it's cooled down. So at optimal time delay, the screening is minimized, and the ablation threshold for the second pulse is decreased. So ablation rate is then much higher, and by this fact, we can then do some enhanced analysis of the materials. We can also do that with cavity ring spectroscopy. This is the case when we perform the ablation of titanium in vacuum. And here's obvious at the same time window, at the same distance, we didn't see much with first laser. Sorry, I don't see where is my cursor. And when it's laser plasma produced with just second laser, you can see that there is just small spectrum, but for optimal time delay in double pulse mode, the spectrum is very nice and very obvious. Under some circumstances, such absorption lines may be not just Doppler broadened, but also Doppler splitted, because lateral velocity component became lateral with respect to detection axis become significant. So as you can see here, ablation angle is then significantly increased, and parallel component of the velocity is now it's become also significant, what may cause also splitting of lines, and by this fact we can then calculate also parallel velocity component of the species. But actually we are interested in can we do more? Can we also somehow determine velocity distribution of ablated species and maybe some other parameters? For that reason, we also did a little modeling. So we described our line, absorption line, with 4 terms. One is related to the velocity distribution, which is usually Maxwell-Boltzmann. So single, double, or sometimes triple mode Maxwell-Boltzmann distribution. Then there is a fact which is related to the geometry, of our system. Then the term which actually describes shape of the plasma plume, which cannot always be represented by some common trigonometric functions. And then term which which depend on the broadening of lines. So usually we have maximum Boltzmann distribution, B model, when fast peak is coming from directly elevated particles from the target, and slow peak are probably can be ascribed to those species which are formed in the plume due to collisional process of dissociation of some other processes, so they are not very fast. The other thing we want to, so we are actually simulating with our model lines which are measured by cavity ring spectroscopy, and then we try to use these common trigonometric functions to describe our plasma plume shape. And actually, this function cosine to the power of 11 worked well, but not perfect. But however, it showed that if this is lateral position of our plasma, that this is full width of half maximum, the plasma is much more velocity component parallel to the target higher. That caused that Doppler broadening of the lines. It actually means that our plasma plume is relatively very difficult, and very good match was achieved of simulated and measured lines when we actually applied cubic Bézier function, which is this line here. This is lateral position, this intensity. What actually means that all particles which are placed here actually are responsible for the Doppler broadening, significant or even Doppler splitting. And this function is, if you compare it with cosine functions, have some kind of top flat. So plasma is actually velocity, angular distribution of plasma densities looks like this. A long time ago, we also performed laser ablation of, as I said before, lithium in different atmospheres. But this work now is also in focus of our interest, because we managed with cavity ring spectroscopy to perform complete mapping of such system. What is now interesting from the aspect of application of cavity ring spectroscopy as a detection for lithium, deuterium, and tritium, probably beryllium at fusion reactor DONES. There was a very nice talk yesterday from Tony Done. And DONES will be used to test the materials for extreme conditions, especially they are interested in testing of materials for very high neutron fluxes. And together with the data collected in ITER, they will then use all of the data then to build demo, which will be, let's hope, source of green energy. So we want to use cavity ring spectroscopy for analysis of exhaust gases, and also as a technique which will be used for cross-checking for other diagnostic techniques of the plasma and of the leakage from the plasma into the exhausting systems. We also applied cavity ring spectroscopy to study plasma jets. It's not topic today, but I will just mention that we also perform detection and mapping of helium metastable atoms along the plasma jet, which is very important species for all those underlying chemical processes in the plasma when it interacts with the material or when it interacts with the surrounding atmosphere. To conclude, cavity ring down spectroscopy then appeared to be a versatile technique to study laser plasma, but also other kinds of plasmas. You can do so diagnostic and analysis of the processes. It's a sensitive technique. It can reach even PPT range, and main advantage is that it can not only detect low concentration of particles, but also particles with low probabilities, transition trace elements, even forbidden states, elements in ground states, which are completely then invisible for any emission spectrum-based spectroscopy. We can also do velocity determination, so not only the parallel and orthogonal velocities, but also we can, from our model, get a velocity distribution and do complete then spatial and temporal evolution of particular species. Cavity ring down is a quantitative technique which allows us to directly determine number densities of particular species in plasma. And then we can also, from our lines, calculate temperatures, latent densities, and so on. And it is complementary analytical techniques to other techniques like laser-induced breakdown spectroscopy, optical emission spectroscopy, and time of flight. But I think that with cavity ring down, we can collect much more useful data on plasmas.
Okay.
So this is it. I would like to thanks to my funding agency, this Croatian Science Foundation, where I have two projects mainly related to laser plasmas produced in liquids for synthesis of colloidal solutions of nanoparticles for then various applications. There is also Eurofusion. I hope they will accept my task, and then I will build a detector for lithium and tritium in the one of the line for exhausting gases. And also we get an infrastructural big project called Center for Advanced Laser Techniques that we will next year buy brand new lasers, spectrometers, chambers, and so on. And it will enhance our investigations. And this is my favorite. Thank you for your attention slides. So thank you for your attention.
Okay, Nikša, thank you for your lecture. It's time for the questions. I see in chat that we have already one question. Sebastian Brezines, please.
I don't see that question.
I can see.
In chat we have announced one question.
Sebastian, you're unmuted, please.
Yeah.
We hear you.
Hello. So.
Yes, please.
So what is the question?
Okay, so I have actually two questions. Question number one is, you mentioned the double pulse, which is quite interesting, but can you indicate what type of delay you had and what type of laser? Is this the same type of laser, or is it one for preheat and a shorter one, let's say later on? So what did you use? That's the first question. And the second one is just to your mention that you will use something for lithium and tritium. We had a proposal and a discussion to use also this technique for tritiated ammonia, but this didn't work out so fine. And I think you might have been involved in this with your colleagues in Slovenia under Eurofusion. So maybe you can comment on this one. Okay, thank you.
Okay, so so we used nanosecond neodymium-Young lasers. Both lasers are nanosecond neodymium-Young with 5 and 4 nanoseconds of duration. And typical delay times, optimal delay times are around 1 microsecond. So for shorter delays, there is screening with first plasma, and for large delays, there is no decrease of ablation threshold because the target is cooled down.
Yeah, thank you.
Okay, so what was the second question?
The second question is, do you see a perspective to use this for tritiated ammonia, where you may have different compounds? This is important for exhaust in fusion reactors if nitrogen is used.
I think there is some possibility to also use cavity ring down to detect ammonia. But I don't know which wavelength. You can also have cavity ring down working in infrared for detection of molecules, but in that case you need femto laser, and in that case the situation is very complicated due to demand for very, very high stability of the system. My system is robust, more or less.
Okay. Thank you.
But do you know Miran Mozetic?
Yes, I know
He
Miran.
tried to do some cavity ring down in, I think, Azdex.
Yeah, this is why I'm asked, because it failed, and it failed for deuterium. If you have a reactor, you will have. If you have a reactor, you will have tritium, And then you will have mixed molecules, which have even more complex, let's say, structure. And you may even don't know where to look at because it's NT2D and something like this. So I thank you for the answer.
But I think the failure was they didn't manage to make setup. That was the problem.
Okay, thank you.
Thank you for questions.
Okay, is there any more questions? If not, I would like to thank.
No more questions.
No more questions.
No more.
Okay.
Okay.
If not,
Thank you and
I
bye.
would like to thank our lecturer, Niksha, for nice lecture. Thank you again.
Bye.
Bye. In continuing, we have another topical lecture. Our next speaker is Deiji Kato from Japan, National Institute for Fusion Science. Is it here, Deiji? Do you hear me? Yes.
Yes.
Yes, please start with your lecture.
Can you see this?
Yes, we can see.
Okay. Thank you, Mr. Chairman. Hello, I'm Daiji Kato from National Institute for Fusion Science in Japan. First of all, thanks to organizers to giving me this chance. This is the first time for me to attend this SPIG meeting. Let me introduce just briefly, our institute. Our institute is Inter-University Research Institute for Development of Nuclear Fusion Plasma Science, which was established about 30 years ago. And our institute is located almost the geometrical center of Japan Island. And it should not be confused with Tokyo. Our institute is located in Toki City. And our institute is situated in very quiet atmosphere, the top of mountain. And there is one of the world's largest accelerator magnetic confinement fusion plasma device, LHD. And the Toki City has more than 1,000-year history of pottery making, and it is famous by one of the picture of a kind of minnoware. I hope some of you will visit us in Toki City in the future. Okay, this is a table of my contents of my talk. First, I will explain background and motivation of our study, and then I will introduce our experiment device, compact electron beam ion trap, COVID. And I would like to share some results of spectroscopic measurements with COVID. Today, I will present two topics. One is electron density dependence of EUV spectra of iron 13, 14, 15, which is related to the diagnostic purpose of solar corona. And the other is about those resonance lines of chromium like tungsten, gold, and bismuth ions, and summarize. So let me begin with the very basic things about what is multiply charged ions. So this diagram is to show what is a multiply charged ions or highly charged ion. So here they are positively charged, which have less number of bound electrons than the atomic number by more than 1. And there are two sequences for groups of multiply charged ions. So one is along the orange line. This is called as nuclear sequence, number of bound electrons is decreasing while nuclear charge is constant. The other is a long red line. This is called as isoelectronic sequence. Nuclear charge is increasing while number of bound electrons is constant. The latter group of the ion is often referred to as element A-like ions. In cases the number of electrons is much less than the nuclear charge, it is called highly charged ions. For both cases, valence electrons are moving in much smaller orbitals, and ionization potential energy becomes larger as charge state increases. And ionization cross-section becomes smaller and the electron capture cross-section becomes larger with charge state. So therefore the high energy and ultra high vacuum environments are required to exist. It is known from all time that such multiple charge ions exist in space, such as stellar corona, supernova remnant, and planetary nebula. On the ground, we observe multiple charged ions of heavy elements in fusion plasmas and laser plasma UV light source. Initially, compact electron beam ion trap operating at energies between 100 TeV to 1 kiloelectron volt was developed at University of Electrocommunications by Professor Nakamura and the Inter-Institute Collaboration Program. The program is aiming at development of validated atomic models of iron and tungsten multiply charged ions for diagnostics purpose of solar corona and fusion plasmas. Later, the second COBIT was constructed at NIFS, and it has been used widely for inter-university collaboration for subjects relating to fusion and astronomical plasmas, and advanced UV light sources and fundamental atomic physics. So electron beam ion trap consists of penning-like ion trap and high density electron beam from an electron gun. Ion trap is made by axial potential well created by an axially applied voltage and radial space charge of electron beam compressed by strong magnetic field of Helmholtz type superconducting magnet. Ions in the trap are successively ionized by electron beam up to a certain charge state. The maximum charge state is determined by the electron energy. Ultra-high vacuum condition is maintained in the trap in order to reduce charge exchange with residual neutral gas. The first EBIT electron beam ion trap in the world was developed at Lawrence Livermore National Laboratory in 1988 for spectroscopy of trapped highly charged ions, based on electron beam ion source developed previously in Dubna in 1969. In Japan, the similar EBIT operating at higher energy up to 200 kiloelectron volts, which is called as Tokyo EBIT, was constructed in 1997 at University of Electrocommunication in Tokyo. COBIT is designed to operate at energy about 100 GeV to 1 kiloelectron volts. This energy range largely overlaps with electron temperature of solar corona and H and Livata plasmas of ITER. You may know ITER is a big tokamak fusion device whose central plasma has a temperature as high as 10 kiloelectron volt, which is now being constructed in France. In base cell components, diverter of ITER, tungsten material is used. Therefore, primary heavy impurity in ITER would be tungsten multiply charged ions. Typical electron density of COBIT is around 10 to the 10th per cubic centimeter, which overlaps with that of solar flare. And high energy EBITs like Tokyo EBIT operate at higher energies and densities, which partially overlap with eta core plasmas. Therefore, EBIT parameters fall into the intermediate region, which complements solar corona and fusion plasmas. Okay, and the charge state distribution in eta is determined by balance between electron impact ionization and combination with electrons in the electron beam. Therefore, electron energy or velocity distribution has a crucial role to determine charge state distribution. In thermal plasma, kinetic energy of electrons is represented by Maxwell-Boltzmann distributions. On the other hand, kinetic energy in EBIT is almost monoenergetic. A typical full-width half maximum of electron distribution in COVID is only 5 electron volts. So this makes the charge state distribution very narrow, that is truncated at a certain maximum value determined by electron beam energy. Although charge exchange with residual neutral gas coexists in the trap may shift and broaden the distribution is sharply peaked around the maximum charge state and can be in principle tuned with electron beam energy. Because of this, charge state identification of emission line spectra in EBIT is much facilitated and more definitive. Also, modeling of spectra is much simpler in principle. So this is spectra measured with COVID, showing a narrow charge state distribution of iron. So by changing electron beam energy, spectra looks different, reflecting changes in the charge state distribution in the trap. So this is the charge state distribution of the iron in the trap, inferred from the emission line spectra. And you see the charge state distribution are sharply localized near the maximum charge states. Okay, so let's move on the first topic. The plasma parameters of solar corona and flare are evaluated in terms of EUV spectra of iron highly charged ions, which increases understanding on dynamics and the origin of solar activities. Observation with EUV imaging spectrometer on board Hinode satellite, which was launched in 2006, is providing highly resolved emission line spectra of highly charged iron ions in corona. So we measured the EUV spectra due to 3D 3P transitions of iron 13, 14, and 15 in the same wavelength range of the EUV imaging spectrometer of Hinode satellite. And EUV line ratios of those ions clearly show electron density dependence, which is useful for diagnostics purpose. And so although our spectra resolution with COVID is not high enough to resolve each blending lines, we could evaluate influence of blending in the line ratio. So this figure showing the results, the line ratio obtained with electron beam energy of 400 and 500 eV are plotted as open and closed symbols. And we plotted also the previous results by Yamamoto and Yang for iron 13. And collisional radial model calculation for the line ratio are plotted by curves. And we obtained the reasonably good agreement between the measurements and collision relative calculations. However, for the iron 15, measurements disagree with the model calculation and show a much steeper density dependence. So further improvements in the model may be necessary. And this is a brief explanation about the model calculation, collision-related model of emission line spectra. So collision-related model, we assume the quasi-stationary state approximation of the population of the excited levels at the given electron temperature and density. And this model includes a very complicated atomic process in the plasma, collisional excitation, de-excitation, spontaneous radiative decays, and ionization, and recombination. And we solve this rate equilibrium equation, taking into account the detailed atomic data. And electron impact excitation rate coefficients used in the CR model was assessed for the line ratio of iron 13 through a wide range of electron density, incorporating results of observation by Hinode satellite and LHD. Solid line and long dash lines results with R matrix and cross coupling calculation of collision strengths. So they agree better with observation, especially at the high density limit. LHD results is below the line, but this is probably due to blending with O5 coexisting impurity in plasmas. And we investigate electron density energy dependence for the problematic iron 15 line ratio. And since electron energy in COVID is almost monoenergetic, we observe resonance excitation effect very clear, as shown here. And although theory predicts the resonance position quite well, the model still underestimates the line ratio, assuming the typical electron density in COVID, so 10 to the 10th per cubic centimeter. So it is problematic that the current model cannot explain the line ratio of solar flare observed previously Skylab also. So this line ratio, so undershoot from the current model. So certainly we need further examination. And the next topics is the search for the resonance line of alkaline-like sequence. The resonance line of alkaline sequence is strong and well isolated in the emission spectra, and it is simple interpretation of intensities in terms of ion density, so which is particularly useful for plasma diagnostics. So far, lithium, sodium, copper sequences have been studied very well and observed in various plasmas. And promethium has a 4f electron shell, which is a loosely bound outermost orbital in a screen nuclear field. The atomic number increases along the promethium isoelectric sequence. The 4f orbital energy falls beneath the 5s orbital energy, as in the hydrogenic system, because screening of nuclear fields by ambient electrons becomes less significant for highly charged ions. Curtis and Ellis in the pioneering work predicted the promethium sequence has alkaline metal-like round configuration for heavy elements. So they should produce a strong 5p and 5s resonance line. And follow-up studies by fully relativistic calculations predicted the level crossing in between z equals 70 and 78. However, in spite of many experimental and theoretical works devoted to seeking for the resonance line emission spectra of heavy elements, there has yet to be a quite definite identification of the predicted resonance line. So we measured permission-like spectra for tungsten and gold and bismuth in UV range, where the resonance lines are predicted. And we found, although the ground state of gold and bismuth is 5s, so alkaline-like, all of the prominent lines are assigned to 5s, 5p to 5s square. It's not resonance line. So resonance line is very weak, always very weak, observed here. You can see here. So this indicates nearly complete population trapping to the long-lived metastable states of 4F13, 5S2, which can only by the electric octapole transition. So lifetime is about 60 seconds for bismuth. And we look into detail what's happening. So this is expression for the equilibrium fraction population for level I, which consists of 4 components. So collisional inflow of the population and radiative inflow of the population, and collisional outflow and collisional radiative inflow to the level I. And this is calculated results for ground level and metastable level. And so for both cases, the population is dominated by the radiative inflow. But the inflow of the metastable state is almost balanced with the collisional outflow, right? And on the other hand, for the ground level, this radiative inflow is very, very small comparing to the metastable level. So this is the reason why the dominant fraction population is made in the metastable levels. So population in the metastable state is more than 10 times larger than the ground level. And however, there is a problem for the tungsten spectra. The prominent line of the probatium-like tungsten we have observed with COVID assigned as lines of neodymium-like. One charge stays higher in measurements with an EBIT reported by the group of Fudan University, Shanghai. And this is partly due to difficulty in correct modeling of the spectra for probatium-like tungsten. Indeed, our model calculation could not reproduce whole spectra of our measurement unless assuming extraordinary smaller electron density in COVID. And recently revised model calculations for probatium-like tungsten by tuning configurations, including the model was performed by Dean, our collaborator in Northwest Normal University, Lanzhou. Apparently better agreement with both measurements at the correct electron density. You see here. However, some lines apparent in the model are not, for instance, this, are absent or very weak in the measured spectra. So we need further investigations. Okay, let me summarize my talk. So model validation for emission line spectra of multiply charged heavy ions and the assessment of atomic data are important for diagnostics purpose of astronomical and laboratory plasmas. The compact electron beam ion trap, COVID, is playing an important role to facilitate the model validation and assessment of atomic data for highly charged ions. The correct modeling of emission line spectra of multiply charged heavy ions are still challenging topics, which is demonstrated the present two topics: density dependence of the line ratio of iron 15 and permission-like tungsten spectra. Okay, thank you very much for your attention. Sorry, I cannot hear you.
Thanks very much.
Thank you.
Okay, do you hear me?
Yes.
Thank you very much for your nice question. It's time for question of another attendee. If you have any questions. Okay. Okay, I have one question. By using monoenergetic electron beam, you can achieve very narrow charge state distribution of produced ions. What is typical ratio of numbers of ions in different charge states in this distribution?
It's yeah, hard to say typical. It depends on the pressure of the residual neutral gas.
Yeah.
So we are always monitoring the spectra for some reference lines. The charge state is already known, monitoring the charge state distribution inside the COVID. And usually we controlling the charge state distribution by changing the flow rate of the gas inlet, I mean target gas. If the pressure of the incident gas, target gas is too high, the adhesive distribution becomes very broad and highly charged could not be created. So we are yes tuning and always monitoring to get the good spectra.
Yes. Okay. Is there any more question? Okay. If not, I would like to thanks again for your very nice question. Thank you.
Thank you.
Okay. Now we will continue with another lecture. It is progress report. Progress report will be given by Sanja Živković. She comes from Vinča Institute of Nuclear Science, and headline of her lecture is analytical capabilities of TCO2 laser base lip setup. Sanja, please start with your presentation.
Thank you for the nice introduction. First of all, I would like to thank the organizing committee for giving me this opportunity to speak today about analytical capabilities of transducer excited carbon dioxide laser base leaf setup for the analysis of the solid samples. So this, something is wrong, I'm sorry. Couldn't change the screen. Okay, this is the short outline of my presentation. First, I will make a quick introduction to the applied technique from the point of view of the analytical chemist. Then I will show you our lab setup installed in Vinča Institute, following with some results of the analysis of the solid samples. And at the end, I will finish my presentation with some conclusions. So, laser-induced background spectroscopy is a relatively new technique that uses focused laser beam to ablate a small portion of the sample, vaporize it, and generate the plasma. If the optical emission from it being analyzed, we can get the elemental composition of the sample. Comparing to the standard methods, analytical methods like ICP-OS, LIPS can provide fast and real-time on-site and remote analysis. It has the ability to analyze all the samples from periodical table in gas, liquid, and solid samples. With the minimal preparation, sample preparation, a small amount of the sample required for the analysis. it can be almost non-destructive with the possibility of spatial and depth analysis. So analytical performance of the LIPS depends on many parameters, such as laser pulse parameters, sample characteristics, especially surface morphology and optical reflectivity, as well as surrounding atmosphere. So the qualitative analysis can be pretty much straightforward without previous preparation of the sample. In the case of quantitative analysis, we have a main complication induced by matrix effect. This effect can be reduced by using the matrix match samples for the construction calibration curves, but these type of samples are not easy to obtain. The other approach that can be used is known as calibration pre-ellipse. It uses some mathematical approaches, but is not it cannot be achieved with our ellipse setup. So in 2015, I have joined the group Dr. Milan Trtica in the Vinci Institute. He completely constructed and designed this laser. You can see this slide. And major characteristics of the laser are given on this slide. What is the difference between the general ellipse setups and our setup is that neodymium YAG laser is used in the most ellipse setups. The difference between neodymium YAG laser and our carbon dioxide laser is regarding the working wavelength of the laser and the temporal profiles of the laser impulse. So you can see here that the average neodymium YAG laser lasts about 10 nanoseconds, while our carbon dioxide laser consists from the initial peak that lasts about 100 nanoseconds, following the long-lasting tail that lasts about 2 microseconds. So this longer wavelength allows us a greater heating of the plasma plume through the inverse Bremsstrahlung, while this long-lasting tail provides additional heating of the plasma and increasement of the excitation. The other difference between our ellipse setup and generally used ellipse setups is regarding the spectral acquisition methods. So in our experiments, we replace the temporal resolution with spatial resolution. It's based on the fact that intense continuum is mostly emitted from the part of the plasma close to the sample surface. By choosing the original plasma and project it directly parallel to the entrance into the monochromator, we can observe the region of the plasma with the highest signal to background inertia. This is our ellipse setup with the major components. What's important here is that the sample is put on the sample holder, which is connected to the rotating motor. This is very important because with every single shot, the fresh area of the sample is analyzed. The optical emission plasma is projected on the monochromator and analyzed with CCD camera with acquisition time from 30 to 60 seconds. So about results, when I joined the group with Dr. Milan Trtica, this was the first experiment I was involved with. The idea of it came from the rover Curiosity, which landed in August 2012. What is interesting about it is that he has on this picture you can see the ellipse setup known as CAM-CAM, and it provides the first ellipse analysis beyond Earth. So what we wanted to show is that maybe our carbon dioxide laser can be a solution for this kind of experiments, since the atmosphere on the Mars consists of about 95% of the carbon dioxide. So what we do, we use the sample of the basalt rock, put in the vacuum chamber, and simulated Marshall condition, and reduce the pressure to the 10 millibars. You can see here that we tested the influence of the laser energy, and we get the most voluminous plasma with applied energy of 160 millijoules. Also, measure intensity by time integrated method. And what we can see is that with increasement of the energy, we have increasement of the line intensity, both for the atomic and ionic line. Also, we will optimize our T-zero ellipse measurements by selecting the plasma region, which will be projected through the entrance of the monochromator. This spectra is average spectra recorded on of the plasma region about 4 millimeters away from the sample surface, and this one recorded about 10 millimeters away from the sample surface. As you see, the better signal to background ratio was achieved at this location, so other experiments will continue using these parameters. So what we do next, we analyzed several spectral ranges, detected many elements, major and minor, and what we want to do is that to compare our results to the results reported in literature obtained by the other authors under simulated material conditions in laboratory. So I don't see because I have the screen with me. Here is the formula that we use where the concentration is obtained by the reference ICP-OS analysis. What we can see that results are comparable and even better for some minor elements. Next thing, what we wanted to analyze is spirulina, which is blue-green algae, used as a food supplement, and it's labeled like a food for the astronauts because it's rich in proteins and minerals such as iron. So we first perform a qualitative analysis of the spirulina. We sent our same sample to the National Institute of the Laser, Plasma and Radiation Physics in Romania, Margoele. And you can see here the several obtained spectra with two different leap systems and two different applied energy with the commercially available leap system. And it's interesting that we didn't get any iron line with the commercial leap system. So what we do next, we always, again wanted to compare our results using the limits of detection. On the left side, you can see the profiles of the calcium line. You can see that our line is better resolved with a lower background emission. When it's about our limits of detection, we're all lower than those obtained with the neodymium laser-based leap system, so we can conclude that our system is better for analysis this type of samples in air at atmospheric pressure. So next thing, what we did, we prepared the calibration standards, matrix mesh calibration standards, using the different another spirulina sample. By mixing dry sample with the liquid solution of the analytes, we did the ICP-OS analysis to get real concentrations of these analytes in the pellets that were made and used for the LIPS analysis and construction. We constructed calibration plots to see is there linear dependency between intensity and concentration present in the sample. These calibration plots are used to determined concentration is in our first sample used for the qualitative analysis. And here in the table, we have summarized our results for the ICP-OS analysis, LIPS analysis, limits of detection of the LIPS analysis, and limits of detection reported in the literature. As you can see, the great agreement was achieved between these two methods, but most importantly, our limits of detection in some cases are lower than those reported in literature obtained with the neodymium-based LIPS systems. The second thing, what we wanted to do is that to apply additional method for the reduction of the matrix effect. This is known as a standard addition method. And for this purpose, we used a peppermint tea sample. Sample was milled, sealed, and homogenized. Different amounts of one essential, one non-essential element was added for in any of it. We made pellets for the LIPS analysis and perform distillate LIPS measurements in air at atmospheric pressure. This is experiment parameters, and you can see the very good aligns with the low background emissions achieved. And the further experiment was continued with manganese and barium. So for the quantitative analysis, we wanted to test three different approaches. So we used just a line intensity and spike concentration to construct calibration plots. The second one, we use line intensity of the analyte normalized to the background. And the third one, we use the line intensity normalized to the line that is present on the spectra, but is available naturally in the sample, which was in our case strontium. So on this slide, I have three basic equations for the calculation of the estimation concentration in the sample, formula for the calculation of relative error of our method, and recovery formula, where is the C reference is obtained by ICP-OS analysis, and it was treated as a true value. What we can see from these results that the normalization approach gives us more reliable results, more accurate with a lower relative error. So next thing, what we want to do is the analysis of metallics, which can be really hard because the most metals have high reflectivity to the wavelength of our carbon dioxide laser. But Dr. Miloš Momčilović found an easy way to overcome this problem. If the surface of the sample is pre-treatment by mechanical treatment of the sample surface, LIPS analysis can be performed. So we use 8 reference aluminum standards, one control sample. Prior to radiation, they were treated with the current sandpaper of granulation of 400. We optimized our 3 cellular LIPS measurements. You can see the other parameters of this experiment and recorded spectra of interested analytes. Using this spectra, we constructed again calibration plots and used it to determine concentration in one reference sample, which is not included in this calibration, and one our control sample. And furthermore, we wanted to see, is there a difference between the accuracy or between the LIPS method and standard ICP-OS analysis method, and we get a great agreement between it. Then in 2016, we get opportunity to participate in second LIPS International Laboratory Comparison organized by the LIPS 2006 16 conference and Bonn Institute from Germany. We get 10 samples, which 3 had a known concentration of nickel, chromium, and copper. We perform TCR Lips analysis. You can see here that the sample was glued on the sample holder, and we calculated concentration using these calibration pods, and we get this certificate of participation that proves that our Lips measurements are accurate. So to conclude, a Lips setup based on TA carbon dioxide laser and non-gated detection has been developed in the Vinci Institute. The proposed Lips setup is lower complexity and cost compared to the standard Lips setups based on neodymium mag laser and time-gated detection. Our results confirm that in respect to its sensitivity and precision, proposed Lips method can be successfully applied for quantitative analysis of macro and microelements in all kinds of solid samples, especially powder samples. Thank you for your attention.
Thank you, Sanya, for your lecture. Now it's time for questions. Is there any question? Please?
No questions so far.
Okay. I would like ask one question. You mentioned that you can also determine the hardness of materials in your recent papers.
Yeah.
What method you use and what is degree of precision in determining the hardness of materials?
It is not precise like the standard method, like the Vickers method, but it can be used for the fast analysis, especially when you don't want to destroy the sample. Vickers method make some small indentation on the sample, which in, for example, analysis of the cultural heritage is not acceptable. While when we use Lips, the very small amount, it's only visible by the naked eye, but with the profilometric analysis, microscope analysis, you cannot see the difference on the sample surface. Is based on it can be connected on the ionic to atomic line ratio, and as the sample is harder, that ratio is going up.
Okay, I'm satisfied. Is there any question? No. If not, I would like.
No questions.
Okay, I would like to thank Sanya again for a very nice lecture. Thank you again.
Thank you.
Okay, and now it is time for a lunch break. We will continue with our sessions at 2:30 p.m. Okay, thank you everyone for coming. Bye.